In this video, I'm going to focus on the terms and concepts associated with the oscillations unit. Within oscillations, there is a specific motion we need to define. This is known as simple harmonic motion and is often abbreviated as SHM. This is an oscillatory motion in which a restoring force is proportional to the object's displacement. Within this definition, there are a couple things that stand out. First, oscillatory motion. This is when an object moves back and forth across an equilibrium position and with the same motion over and over. I'm representing this equilibrium position with the dashed purple line. So when we have this block tied to the spring, sometimes it will be on the left of equilibrium, sometimes it will be on the right. It's going to oscillate back and forth over and over. We'll define equilibrium mathematically as where the position of the block is zero, and this is also the object's resting position if it were to come to rest. The second thing that stands out is with restoring force being proportional to displacement. Now, restoring force isn't a new force that you have to learn. It's just saying that one of the forces from your force diagram is always pointing towards equilibrium and therefore trying to restore the object to that midpoint. In this example, that would be the force from the spring. If I smush the block into the spring wants to kick back out, back to the right towards this line. If I pull the spring out to the right, then the spring is going to try to pull its way back to the left, always trying to restore itself back to equilibrium. Mathematically, we describe this with Hooke's law. It's stating that F is directly proportional to X, they're on either side of the equation, and the negative is there for direction. Whichever way we change X, F is going to be acting in the opposite direction. When it comes to solving problems in this unit, you're going to run into two common setups. We've already mentioned the mass connected to the spring, but now we're also looking at the pendulum, which is a mass at the end of a string. Imagine we pull the mass back and release it. It will next swing back and forth across our equilibrium line. Now in real life, we would expect these objects to come to rest pretty quickly. That's because damping forces would be present, things like friction and air resistance. But in this level of physics, we aren't considering damping forces, as they're too complicated to study with this type of motion. Instead, we'll expect objects with simple harmonic motion to oscillate forever. Here we're looking at terms and their definitions. Let's start with period. It's the variable capital T, and we first learned about this back in our uniform circular motion topic. This is the number of seconds that it takes to complete one revolution. In a simple harmonic motion sense, that's to go there and back. Frequency is lowercase f. This is the number of revolutions that occur in 1 second. We can measure that in hertz. Think of it as the inverse of period. Period is seconds per revolution. Frequency is revolutions per second. Angular velocity is the Greek letter omega. This is the rate at which an object revolves or oscillates. We measure that in radians per second. And amplitude is capital A. This is the length from equilibrium to the maximum position the object reaches away from equilibrium. We measure it in meters and know that it's a scalar. This will always be a positive amount. Next, looking at an equation. This is more of a conversion. If you know any of the variables period, angular velocity, or frequency, you can use this equation to find the others. Finally, I want to talk you through a position versus time graph for this type of motion. I'm going to use the graph to explain an equation. Before we construct the graph, look at our situation. We're releasing an object from rest at position x1. The spring is compressed. It's going to push the object to the right. We'll expect it to extend out to x3, pull back to x1, and this will go back and forth over and over between those positions. As far as the graph is concerned, we want to make sure that it has two quadrants, a positive and a negative. Remember, the equilibrium position, which is x2, is where our position is 0. Because we can go to the left side of that and the right side of that, we would have a negative and positive category. It doesn't really matter which you call which. I'll just place x1 as our positive and x3 as our negative to get started. As we construct the graph, let's start by analyzing the y-intercept. The block starts at x1, as does the graph, and because the block is released from rest, we would expect the starting slope of our position time graph to be horizontal or 0, because the slope means velocity. From there, the object goes out to x3 and back to x1. You can see it going back and forth across our equilibrium line. And because the line is constantly curving, that's explaining why the object is speeding up, then slowing down, then speeding up, then slowing down. It's always flipping back and forth between those. So we get this cyclical graph, and it's easy for us to then pick out how many cycles it's completed. There are a few things that we can extract from the graph, starting with amplitude. Amplitude is the measured distance from equilibrium to the maximum position away from equilibrium and represented by the purple bar. Period is the time it takes to complete one cycle, or one there and back revolution, so to go from x1 back to x1. And if we know period, we can always quickly convert to frequency. From there, we can look at the position as a function of time equation for simple harmonic motion. You can see that amplitude and frequency are represented, and this would match the cosine shape of a position time graph. If instead your position time graph is of a sine shape, you would want to flip the cosine function with sine, but it's the same equation. And know that for these equations, since pi is included, you would want to flip your calculator to radian mode.